Hello everyone, myself Prashant. Topic for today is the abridgment of the VLSI. At the end of this presentation or video, one can have an idea of what is VLSI and what are the various steps involved in order to develop an integrated circuit. What are the various kinds of transistors which we can use or which we have been using in an integrated circuit, and some of the case studies related to VLSI and the job opportunities for a person who choose VLSI as his or her career. Let's move forward without any delay. Following are the topics covered as part of this presentation: what is VLSI, evolution of various transistors used in the VLSI, the basic ASIC flow, and the role or importance of a physical design engineer. So at this point of time, I would like to say that I am a physical design engineer who is in the industry for the past 7 years. Okay. The latest trends in the lower technology node, which we are following, some of the case studies and the job opportunities at the end. What is VLSI? So VLSI is an acronym for very large scale integration. VLSI is an acronym for very large scale integration. So one will be developing an integrated circuit. So as part of the VLSI, one will be developing an integrated circuit. So if any of the audience is from the electronics background, so you might be having an idea of a circuit. So basically IC, integrated circuit, is like different components soldered together in order to achieve some functionality. So if you might have remembered in the electronics labs, like in the digital logic designing lab, you might have designed the clippers and clampers. You might have used several transistors and resistors or capacitors. You might have put it on the breadboard, and in order to achieve one functionality. So it's like I can say this is one kind of integrated circuit. So not only that, so the one which we are using in our mobile processors or in your laptops or any electronic gadgets, so that is nothing but the processor. The processor is nothing but an integrated circuit. So I can say like we'll have both active and passive elements in an integrated circuit. So some of the active elements like bipolar junction transistors, CMOS, and some of the other transistors which we have. So we can call them as an active elements, and the passive elements like the diodes, capacitors, and resistors. So these two together will form a circuit, and we call it as an integrated circuit. So, but I'm saying that both, whatever you have developed as part of your lab or digital logic designing lab, the clippers or clamper circuit, and also whatever the processor we have, is both of them are an integrated circuit. But what decides what is the basic difference between these two things? So I can say that the complexity decides the type of the integrated circuits we have. So we have some of the types of integrated circuits. So the first one being small SSI, it's small scale integration. If at all we are having 10 to hundreds of transistors in our circuit, so we call it as a small scale integration. So next one is MSI or medium scale integration. If at all we are having some hundreds to thousands of the transistors in our design, we call it as MSI or medium scale integration. And then coming to LSI, the large scale integration. So if at all we are having greater than 10,000 of transistors in our design, we call it as an LSI circuit. And then our focus, VLSI, very large scale integration. If at all our chip or a circuit is having around 1 million of transistor or more than that, we call it as a VLSI. The typical chip will be having like more than 1 million of transistors in the current designs. So whatever it may be, it can be artificial intelligence chips or any graphic processor or SoC or anything. So it will be having like more than 1 million of transistors inside that. So BJT, CMOS in our integrated circuits. So BJT, bipolar junction transistor, you all know that it is a current control device. So basically BJT offers high speed, more gain and low output resistance. So whenever we wanted to achieve a functionality where performance is the most priority, so we can just opt for the BJT. So but it has its own limitations too. So basically we will be using this BJTs mostly as part of my analog devices or analog designs. And then CMOS. So CMOS offers high input resistance and better for low power logic gates. So in our digital world and in our digital designs, we'll be using this CMOS. So because of its own advantages, we'll be using this CMOS things inside it. Okay, let's move on to the next one. Evolution of various transistors we have used or we have been using so far. So let's start with the planar CMOS. So planar CMOS, so you can see on the screen how it is looking like. It's on one side you're having the source and the other side you're having the drain, and on the top you're having the gate. So you know CMOS is the voltage control device. Whenever you apply some potential to the gate, the channel will be formed underneath that in between source and drain, and it enables transfer of electrons from the source to drain, and that's where we call it as the switch is on. CMOS is acting as a switch here, and switch is on, and it is uh, like we can see the output now. So when we apply some potential and that potential to the gate, when that potential is greater than the threshold voltage, only then we can say the channel is formed underneath that and the transfer of electrons is happening. So I'm saying that it is a horizontal channel here. The planar CMOS is having the horizontal channel. So horizontal channel in the sense the source and drain are at the same level and the gate is above that. So as I said to you, the gate or the CMOS is a voltage control device. So we are having we are applying the potential to the gate, and it's like the formation of the channel is only controlled from one dimension, so which is nothing but the from the top. So that means from the top, based upon the voltage which is applied to that, the channel will form, and so that's why we say that the control is from only one dimension. So earlier ICs, most of the earlier ICs are made up of the planar CMOS. So but what happens as the technology node is shrinking? Okay, so for the some of the guys who is new to this, so I can say that based upon the channel length, we will say we will decide which technology node it is. So you might have seen like 180 nanometer to 50 nanometer technology nodes also. So that means 180 nanometer to 50 nanometer is nothing but the channel length which we have. So the channel length, based upon the channel length, we say the technology node. So that means if the technology node is shrinking, the channel length is reducing. So when the channel length is reducing, the area which my gate is going to cover is going to reduce. That means it is nothing but we are having kind of limited controllability over the formation of the channels, because the technology node is shrinking. The I mean, so how well or how faster we can prepare, or I mean the how amount of controllability which we have here is reducing. So that's why it happened to move to the next uh, type of design or next type of transistor. So we'll see what it is. So FDSOI. So it's nothing but fully depleted silicon on insulator. So once again it is a horizontal channel. So but what is the difference between planar CMOS and FDSO technology is, so the construction part is different. So as you can see here, we are having kind of ultra thin buried oxide layer here. So we call it as buried oxide because it is underneath the source and drain. So we'll be fabricating this ultra thin buried oxide layer first, and then on top of that we'll be growing the source and drain, and then oxide layer, again one more gate. So the channel which we have here is very thin. So when you compare to the planar CMOS, the channel which is present over here is very thin. So and as the channel is very thin, we don't even need to have or add any kind of doping, any kind of, we don't need to do any doping to the channel, and so that's why we'll call it as it's fully depleted. So that's the reason we call it as fully depleted silicon on insulator. So as I said, the transistor structure won't change, but a thick layer of insulator will be added below the channel. So we have some buried oxide layer present over here underneath that. So that's the only basic difference between that one and this. So leakage will be very less compared to the planar CMOS. So why the leakage is less? So for example, we don't have the planar CMOS. I'm kind of drawing the CMOS how it looks like. So the cross-sectional view of the planar CMOS can look like this. So whenever the channel is formed, so we will have the kind of electron transfer, or the channel is formed and the electron starts flowing. So they can take any path over here. So it can go from here to here, here to here, and also some of the leakage will happen like this. So channel is formed and some of them can even go like this. So now because of this we can say the leakage which we have in the planar CMOS is kind of more. But now as part of the FDSOI, as thanks to the buried oxide layer which we have, we will not see such kind of leakage happening over here. So whatever may be the transfer we have, it will be above this buried oxide. So you can see we have here oxide on the top and oxide on the bottom. So I can say now we kind of have a backgate formed here. So one being from the top and the backgate here is from the bottom. So we have oxide and above that source and drain. So it has one kind of advantage, I can say. So I can say it have better control over body bias and is dynamic. So I would like to explain what it means. So body bias. So first of all, I want to explain what is body biasing. So we have the substrate over here underneath here. So this dark gray color is the substrate. So we will be kind of applying some potential to the substrate, and we call it as a body bias. So substrate is nothing but the body, and body bias or some voltage will be applied to this. So as we have the alkaline buried oxide layer, so body bias plays a significant role, a prominent role over here. So we will be kind of say we'll be having some potential applied over here. So we'll be having some potential applied over here, and it will be connected to my body bias, the body. So now based upon this body bias or body bias voltage, so we can say we can alter the VTH over here. So that means we have kind of better control over the body bias. Not only that, so it is dynamic. So once the chip is fabricated also, we can alter this body bias voltage, and we can achieve, we can operate our chip in the two different modes. So as the body bias can be altered and it is also dynamic, so we can operate. So based upon this body bias, we can say the threshold voltage is kind of varied, or we can alter the threshold voltage over here. So as the VTH can be altered, as the VTH can be altered, I can say, okay, before this, so how the VTH can be altered, because like say, the voltage is the potential difference between two different plates. So now here, these two are kind of say like acting as a plate. So here, so you have the body bias applied over here, and so I can say the VTH can be altered. So what are the two different kind of operations possible? The one being more energy efficient and the other being more performance. So based upon the kind of threshold voltage we have, if it is high, one kind of operation, and if it is low, other kind of operation is possible. But we kind of have similar things possible with the planar CMOS also. So where we are kind of changing the doping concentration, and we have two different types of cells. So which are nothing but low voltage, high voltage, or medium voltage, medium threshold voltage. So low threshold voltage or medium threshold voltage or high threshold voltage we have. So but here the kind of operation which we can achieve is is dynamic, so because it's runtime. So once it is fabricated also, we can kind of change it, and we can use it as per our requirement. So that's why I call it as, I have used the word dynamic here. Okay. Yeah, but because of its challenge, because of the complexity related to the fabrication steps which we have, so it is, it was not, it hasn't become much popular. So ST Micro is the first one who kind of developed this kind of technology node, and then so it was not encouraged, or it was not being used more across the across all the designs. So we kind of developed a new technology, new kind of transistor. So in order to overcome whatever may be the challenges which we are facing before. So let's see what it is. So it is nothing but FinFET. So field effect transistor. So I have put like planar CMOS and the FinFET side by side. You can kind of correlate what is the basic difference between. So both of them are like cross-sectional views which you have. So the planar CMOS is the horizontal one, horizontal channel, as I said to you. But here you see, it's kind of embossed, these dark gray color are the source and drain things. So it's kind of embossed, and from we have source on one side and the drain on the other side here. So but here the basic difference, or the major difference over here, is the gate. So the gate over here is now 3D. So that means it's three-dimensional one. So from the left, right, and top, we can kind of control the formation of the gate. So whereas in the planar CMOS, the control is only from the one direction, that is from the top. So but here in the FinFET, the control is from the three dimensions, which is from left, right, and top. That means we kind of have more or better controllability compared to my planar CMOS. So with this, we kind of increase the controllability which we have in the 3D gate architecture of FinFET. We can increase the controllability of the formation of the gate. So it has high drive currents, by the way. FinFET will have high drive currents compared to my planar CMOS. So it has faster switching times also. So the next one, or the next kind of transistor, is GAA, which is nothing but gate all around. So FinFET being with the FinFET we have a control from three dimensions, but in the GAA gate all around, we have gate in all the directions, from left, right, top, and bottom. We have the gate, and and now the fins are now nanowires. In the FinFET, we have the whatever the fins we have here are they have become nanowires. So controllability is even greater than the FinFET. You can see the formation of the channel is even greater than the FinFET. So you can see here that in this diagram, so how the fins, the nanowires will look like. So here it's like 8 nanometer. So you can imagine how thin this particular thing is. So it's like it's very thin. The diameter of this is like 8 nanometer, and it's very thin, which we have over here. And the kind of the construction which we have over here is kind of very typical, and it will be like more it's like more burden on the process engineer, like it involves uh, in various complex processing steps or fabrication steps here. And we can say we don't know what is the yield which we have, which we can achieve over here. So this is about my gate all around. So let's move on to the next. Before that, so I can show you like all in one picture. So this is the planar CMOS, and it's the double gate FDSOI and the tri gate. So from the top left and right we have them, and here we can see the fins. Okay, and I can say based upon the number of fins we have, the performance will kind of increase, or the resistance will kind of increase. And then we have the gate all around. You can see the nanowires over here. So this is the gate all around and well fed. Okay, so all these whatever we have discussed so far is like everything in the one page we have. And at present we are kind of using the FinFET or the tri-gate architecture. So we are yet to realize this particular thing, and it has some of the complexities involved in that. Okay, so I would like to discuss some of the important fabrication steps as part of fabricating the integrated circuit at the foundry. So the first important step or first important point here I want to discuss is crystal growth. So you all know the silica or the sand is the main ingredient in development of our integrated circuit. So we will take the silica, the pure form without any impurities, we'll heat that at like with higher temperatures, we'll melt that, and we'll kind of form a cylinder or cylindrical shape, and we will then cut that cylindrical shapes into smaller sizes. So after that, so you can see a CD or a disc formed. So it will be just like our regular CD which you have at home. So it will be just like that, but so it is with completely with the help of the silica, and we will use this for developing or for fabricating the transistors in that. So overall, I can say like once that cylinder is formed, we will just divide or we'll just cut into some pieces, and we'll just make use of each of that crystal. So one point here I want to mention about the crystal is, so larger the dimension or larger the diameter of the crystal, thicker it has to be in order to maintain or achieve, or in order to have good mechanical stability. So next is the oxidation. So oxide layer will be used several times or multiple times during the fabrication process, because it has some of the good properties, like so it is good for insulator. It has good insulating properties, it has good dielectric properties, and it has good mask properties. So I'll say what about what I mean by all of these in the next I mean next so photolithography. So photolithography is like kind of passing the UV light and etching the unwanted area. So this is like photolithography. So at this point of time, I would like to discuss, or I would like to show how fabrication will happen. So let's suppose we wanted to fabricate one metal shape, so which is like this. Let's suppose we wanted to fabricate this, and in order to do this particular exercise, or in order to fabricate this particular metal shape, the first thing which we wanted to know or which we wanted to have is a mask for this. Let's say we are having a mask like this. So not only this, so as you want to fabricate this in the middle, let's say wherever we want to fabricate such shape, we will be creating a hole like this. So obviously we'll have the crystal in the bottom like this, and let's assume we have developed uh, the oxide layer on top of that. Let's suppose it is like this. So we will pass the UV light of certain frequency through this mask, and wherever it is passed or wherever it has gone through that particular mask, so I can say that particular area will become soft. So when that particular area will become soft, so and after we pass the required chemicals and etch this process or etch it, so we will see something like this. Okay, I think it is completely gone. I will draw again. So the remaining portion for us will be looking something like this. So the remaining portion which we have will be looking like this. So in this we will be having some empty area present over here. So in that area we can fill it with any metal or with any kind of material we wanted to. So after that, so that's how I can say, like we can kind of fabricate our required shapes, so with the help of the mask and with the help of the photolithography or oxidation process. So this is like one of the important steps in or these are some of the important steps during the fabrication. So it may not like give you complete idea of how the fabrication will happen, but it is like a glance of what is going to happen or what may happen inside my uh, fabrication process. Let's move on to the next topic.